Hi, my name is Junbong Chang, and I'll present how to make an image classifier that can classify black and white boxes with 100% accuracy uh, using a TensorFlow library and in a Google Colab environment. So I recommend using Google Colab because if you don't have any GPUs in your local machine, or if you have trouble setting up uh, the environment, it's best to use the Google Colab for easy setup and a quick testing of the deep learning models. So this tutorial is follows a basic machine learning workflow, which first examine and understand data, build an input pipeline, build the model, train the model, and test the model. So first we set up the TensorFlow and other necessary libraries. So you just press this arrow, this to run this cell. You call this thing cell. And so we imported the matplotlib for drawing a graph, NumPy for doing some operations, PIL for image, which is an image library. TensorFlow is the deep learning library, and Keras is the uh, easy version of TensorFlow, you can say. So it makes it easier to use TensorFlow, basically. Okay, so first we load data using Keras utility. First, uh, we create two things, black box and white box by NumPy library. So in this tutorial, I must emphasize that we are gonna build the 100% accuracy deep learning model image classifier. And that is possible because we are solving a very simple task, which is classifying black box or white box. I think if I remember correctly, that's uh, in other words, a Rube Goldberg machine. So we make a very complex machine to solve a very simple task. But this is good for educational purpose, I think. So we first create black box and white box, and MP zeros. Just create a matrix of zeros uh, with size 128 by 128, but with three channels, and the data type is uh, unsigned integer 8. And the white box is the same, except that we multiply 255. Oh, and also we use MP1s so that we get the matrix of ones instead of matrix of zeros. Okay, and then the next cell, we import the Google Colab drive and mount the drive, which is our, which is the local drive for. So and we just specify the data directory, which I made a folder called images for training in my drive. Okay. So you must create this folder in your drive also. So images for training. Yeah. And then if I just run this and then oh, by the way, if you run it for the first time, it will ask for the permission to access it, access your drive. But I already gave a permission, so I don't get any error. Now if I run this cell to uh, save these NumPy uh, objects into my drive, it will save white box and black box into my drive by this operation in the save into this data directory. And if you check, you will see that in my drive, images for training, you have white box and black box, right? And for setup, you have to create this white and black folder, and then put the image into white box. Also, put the white box PNG into white folder, and put the black box PNG into black folder. You need this so that later on, when you use the Keras library to load image dataset, uh, this requires that each image a different class. must be in different folder. So the white box must be in white in this folder, in white folder, and the black box must be in the black folder. Yeah. So I ran this, and then you define some parameters for the loader. So I set the batch size to be 32. So which means batch size means that in one iteration you train on 32 images at once. And I set the image height, input image height, and width to be 128. Okay. Then it's good practice to use validation split when developing your model. But as you know, we only have black box and white box in our training data set. So for validation, we also use black box and white box. So so we set the train data set as, and we load the train data set from this data dir, which is our drive directory here, images for training. Okay, and then you also load the validation directory, which is the same as above. So now you have uh, data uh, data set object which have two files belonging to two classes, which is very small in usual deep learning deep learning projects, but we only need two for training because the task is very simple. We only classify black box or white box. Okay, so you have two classes, black and white, in our data set. It's probably gonna be the same if you change it to validation data set, because of course we have the same code here. Literally, it's the same code. ValDS, that class names. Let me see. It's different. Somehow it's different. If you can find a class name as a class name in these data sets, this corresponds to directory names. It's class names. Interesting. So somehow ValDS does not have it. Let me rerun it. Okay. Okay. The error was because I didn't run the ValDS. So it didn't know about the ValDS. So now I go to the next step, which is visualizing our data. So I use PLT library to visualize it. PLT figure, just set the figure size, and for each image in our data set, we plot it. Right? ImShow is plotting the image into the figure, and title just set the title of the figure. Axis of just takes up the grid, what is it, the axis, XY axis, remove it from the image. Yeah. And the subplot simply put the white box and black box next to each other. Okay. And you can see that our data set, entire data set, is comprised of white box, 128 by 128, and black box, which is also 128 by 128. Okay. Now you pass this data set to the Keras model.fit for training. But beforehand, we check their dataset shape. You can see that image batch shape is 2 by 128 by 128 by 3, and labels batch is 2 because we have two classes. Okay. Okay, this is not correct. This is from the previous project, so we can remove it. Okay. Now we configure the dataset for performance. Um, we use the buffered prefetching so that we can load the data without IO becoming blocking. So usually loading the data set is a bottleneck in training the data set, in training. So it's best to prefetch the data while the GPU is training on one batch. The pipeline would load other batches uh, ahead of time to prevent any blocking. So you can read all this through, but I will uh, show you this part. Okay, so this thing first caches the data set. Well, so cache means that it keeps the images in memory after they are loaded off disk during the first epoch. And shuffle just simply shuffles the entire data set so that uh, the order does not matter during training. But in our case, it's only white box and black box, so it probably doesn't really matter. But yeah, I just kept it because you should do it in for other data set for more complex tasks. And prefetch is what I just told you. So you just prefetch the data uh, while the GPU is processing one batch. Okay. Buffer size is just auto-tuned. Okay. And so you have train data set and validation data set configured for performance. So you actually probably you don't need this to run this code, but we have it here for performance for your educational purpose. Okay. And we usually standardize the data because the original data ranges from 0 to 55. So it's very big, actually. Uh, so if you standardize the value to be between 0 and 1, uh, the deep learning model, I would say the learning space, uh, becomes simplified and it's easier to, how would I say, train the model. Yeah, the model trains better in simple words. Yeah. So we scale, normalize. We set the normalizing layer, which divides the uh, input by 255. And then we apply this normalization layer to the data set by this mapping operation, right? Normalize X, input X. The label is stays the same. And we map this to the train data set, right? And then if you if you uh, get the one sample from the data normalized data set, you will see that the image is normalized. Remember that each batch has white box and black box. So in this case, the first image was black. So its mean and max are both 0, right? And also in second image is white. So its mean and max are both 1. Okay. Okay, now we create the model, Keras model. We use the sequential library in Keras, which combines the scaling layer, convolutional 2D layer, which and then max pooling layer, and flatten it at the end because, and then pass it to the dense layer. You have to flatten it because uh, convolutional layer works on the 2D feature, while the dense layer works on the 1D feature, one-dimensional feature, right? Here, these parameters represent three, is it the filter size, and the 16 is the number of the filters, otherwise the channel-wise dimension, right? Okay, and the activation is ReLU activation, which is just um, 0 for the negative value and uh, same and input value for the positive value. Okay, and the padding same means that the convolutional layer does not reduce its size. So it tries to keep the size of the feature after a convolutional operation. Okay, so that's what it does. So this is very small deep learning model, but this is enough for our task. Okay, so we define our model and then we compile it using the Atom optimizer. Atom optimizer is uh, widely used, and I also recommend it because it seems to work well in various tasks and dataset. So yeah, for a starter, for beginners, it's good to use Atom, and then you can change the optimizer for more even better performance later on. And then the loss function uses the sparse categorical cross entropy. So the cross entropy is for the classification task, and this takes the logits as input instead of the probability. And the metrics, it also outputs the accuracy as metric. Okay, so we compile our Keras model, and we get the summary of our model here. Okay, the rescaling layer, which reduce the range 0 to 55 to 0 to 1. Yeah, and convolutional layer, and you get this number of 448 parameters, right? And you also have this output shape, right? And then max pooling layer, which reduces the size, input size, the XY width and height by half. And then another convolutional layer, the max pooling, another convolutional layer. And you notice that in each step, in each max pooling layer, you get half the size of the feature map, and also the parameter increase, number of parameter increases because the size of the channel increase for the convolutional feature. And at the end, we flatten the 2D feature and then pass it to the dense layer, which is a fully connected layer, in another word, or MLP, multi-layer perceptron, and you get, and this actually has the most number of parameters. And then lastly, since you have to classify two classes, either black or white, you need to have two as output shape, right? So you have two dense layers. And in total, you have 8 megabytes of parameters. Okay, and that's relatively very small, right, compared to like ChatGPT or other huge models, right? And now finally, we trained our model using Keras, model.bit. We trained it for 10 epochs. Uh, so training data set and validation data. For the validation data, we use VLDS and epochs 10, right? So you can see that training accuracy is half at the in the beginning. So it's actually just random, right? Black or white. That means like that's the worst you can get, accuracy 0.5. But then as training progresses, training accuracy becomes 1 quite that quickly actually in 5 epochs. And validation accuracy also goes to 1, actually even earlier than training accuracy, right? And also you can see that the batch size is just 1, right? Because our data set is only 2 images. So training went very well because we got 100% accuracy. Both training and validation are at 100%, right? And we can plot this result in the graph, right? Because remember we stored our the training log into history variable. So now we can access this accuracy, validation accuracy loss, and validation loss, and then plot it on the line graph here. So, right, this loss is always decreasing, and accuracy goes to 100% very quickly. Right, the task was very simple. So, but in the real world, our data set It's very complex, so you would never get this 100% accuracy. But uh, in the simple world, black black or white world, this is possible. Okay. Now we can predict on new data using our trained model. So for example, we load sunflower image. Here's our sunflower. This is uh, publicly available uh, here in this URL. So this is sunflower. If I use our model to classify black or white, let's see what we get. We get that this image likely belongs to white class with 98% confidence, which is okay. Yeah, sure. But let's say we remember we had black image object, then it should say that it is black image, obviously, right? Black img. Oh wait, let me see. Black box, I think. Black box. Yes, right, black box. Okay. So if I input black box, then our model.predict, must say that the image most likely belongs to black with 69% accuracy. Confidence, not accuracy. The confidence is from this softmax score, this prediction, which is pretty low actually, considering how easy this task is. Let's say I input white box instead. So remember, white box looks like this. Obviously, you don't see this, but this is white box. Yeah. Well, it's white. The background is white, so you can't see the white box. And if I predict what the class is, then the model predicts that the image most likely belongs to white with 99.99% confidence, which is successful. Okay. Well, that's it for this simple tutorial. Uh, and I will share this Colab link, so feel free to play around with it. And if you have any question, ask me in a comment section. Thank you.